was mentioned, as it was mentioned, I'm here in California, so it's just after midnight for me. And I'm looking forward to talking about one of my favorite topics, which is distributed tracing. First of all, I am Dave McAllister. I work for a company called Splunk. Splunk likes to point out that everybody has a million data points, and mine are kind of interesting that I'd like to do this. I spent 10 years as a football, for us in America, soccer rep, so I'm used to people disagreeing with me. And I'm owned by 3 cats, so I'm also used to being ignored pretty well. With that, let me start by talking about why we have this tremendous uptake in distributed tracing these days. And it starts with this concept that's called observability. And observability lets us drive through and understand what's going on here. So it's a new set of data, if you will, that are allowing us to understand the various pieces. But imagine if you couldn't get all the data, or you missed ephemeral data, or your data showed you something you couldn't go deeper into, or you just saw the good stuff or the bad stuff. So distributed tracing starts allowing us to answer some of those questions specifically around that. Now, why do we even care? Well, this is really around this thing, and I love this chart. This is called a Cynefin framework. And as we move into cloud native, there are actually kind of 2 paths that happen here. There are lots of paths, but we usually hear about 2 things: microservices, or breaking down into functional blocks that are as small as necessary, and then a cloud movement, which is allowing us to have the ability to do elastic and ephemeral. When we had a single application running on a single server, we had a very simple practice. We could sense, we could characterize, we could walk down the row and look at the servers and say, gee, are the lights flashing? And see if the server was up or down. As we moved into microservices, things get more complicated. And as we move into cloud environments, things become elastic and ephemeral, so they become more chaotic. Microservices have complex interactions. The pathways through them are there, which means failures don't exactly repeat here. And therefore, as we move into these things, we need to move both of these practices into this complex environment where we are probing for results. We're sensing the responses that are coming back here, and that allows us to respond. So here's a simple microservices architecture. It's an e-commerce front. The internet comes in, it talks to a front end. That front end then can talk to multiple services, and those services in turn can talk to other services. So the front end comes in and it talks to all of the various services that cross this. Each of these services does one or more functional units, and therefore the complexity is twofold. The units themselves can scale, and the communications pathways, that networking communications, can also scale. We're going to have a load generator delivering synthetic models as well, also happening for this. And this is what a trace looks like for that application space here. The front end comes in. It can call a checkout service. Checkout service can then look at what's in the cart. Various pieces go down here. Each of these things happens in time. And so that we have a time series of what happened to a request as it flowed through the system, or to flow through each piece of the system. And a trace itself is actually very simple. It's the single unit of work is called a span. What happens inside that span is the functional combination. In this case, for instance, you can see that my trace, defined by its spans, is made up of 2 microservices, and one of those microservices is actually made up of 2 separate functions. So distributed context comes into play when we start putting the tracing identifiers on it, the tags and options that let us know how we are moving from one span to the next span. The top is called the parent structure, so we have a parent-child relationship as these things call through. Now, similarly to the way we get tracing data, we can also get metrics data inside of here. And our metrics in tracing are usually something that's referred to as RED, rate, error, and duration. become the major players here. But what happens is that we can have impacts that are showing up very quickly on our metrics. So for instance, we see a CPU that's running at 100% in the checkout service that may trace back to a new deployment where we code pushed the front end and now we're handling 5 times or so the number of requests. And this can indicate a couple of different issues that are happening in the application. One, maybe something didn't scale correctly. So we are now not having an elastic effect of our cloud service. Or two, that our front end, the new code that we're doing, has a problem and is pushing more activity than we expect. And so we now need to be able to figure out where the problem is occurring, but also what the problem is being caused by. Likewise, logs play a similar role into here. And we can end up with an increase showing up, in this case, a 503 increase, that's coming from an email service that's also being shown up in a checkout service. So again, where an error is reported is not necessarily where the error occurs. And distributed tracing allows us to take a look at that. So in this light, one of my favorite quotes around this is observability isn't the microscope. It's not the tools we use. It's the clarity of the slide under the microscope. It's the amount of data that we can see so that we can do the aggregation and the analysis, look at the visualizations and the responses. So the biggest thing around this is that data drives this functionality. And so distributed tracing starts with data collection. And I am a strong believer that our data should not be locked in. It should be standards-based data. It should be cloud integration data here. And because of that, we also have some other features that then come into play. It should be automated. As we'll see when we're getting into here, tracing itself, distributed tracing, gives us a lot of capabilities. But if we end up having to hand code everything every time we do a release, this becomes problematic. So we need automatic ways of implementing a tracing structure. We need support for developer frameworks, whatever those frameworks are. We need to be able to make use of any code at any time. The other thing that happens in a microservices environment is that quite often our microservices are not written in a single language. They're written in the appropriate language here. So we need to be able to sort any of these codes in pieces. And then finally, something that's a little more esoteric, a little more out there, is that really we don't want cardinality limits. Cardinality here refers to the capability of being able to do that slice and dice. And so that we can cut the pieces down and be able to drill into them. That this trace came from this particular request, that came from this specific user that's running on this specific AWS instance, for instance, making use of this specific S3 box as an example. So we have lots of places that we want to be able to trace it down. Fortunately, when we get into this, OpenTelemetry has come into play. So OpenTelemetry is sort of the next major version of both OpenTracing and OpenCensus. And OpenTracing sort of started this concept of an open distributed tracing model. OpenTracing defined the series of what we needed to be able to trace and started helping provide the ways that we put tracing in place. Predecessors for this were things like Jaeger and Zipkin. And they were incredibly important in helping define, but they didn't help us with the back-end approach. Google released something called OpenCensus. And OpenCensus took the same construct of a standardized approach for the distributed tracing information, but also provided the back-end capabilities for us to be able to know how to collect it and be able to aggregate it together. The two, of course, were both open source projects. They are overlapping. And at this point, it's been a little over 2 years since the two decided to join together and create OpenTelemetry. OpenTelemetry is a cloud native computing foundation open source project. It is the second most active project in CNCF, And I'm actually very pleased to be working for a company who is the leading contributor to the capabilities of open tracing. We have donated an immense amount of code. We have engineers who continually work to improve open telemetry, and we've even contributed intellectual property in the forms of the agent structures all the way down to the logging specification that we'll get into. OpenTelemetry is the driving force. It is the way that the distributing tracing world is going. And you can see this not only by its activity, but by the adoption that's showing up across lots of available products, as well as use in the open source world itself. So we talk about this thing, this telemetry environment. And telemetry is a piece that's fairly important because we need to be able to take the data in. So telemetry is kind of how and what we collect for this. And the telemetry can break down, in this case, into these two categories of the types of data, tracing, metrics, or logs, for instance, and the layers of tracing, which is the implementation details here. And so for instrumentation, we want each language of interest to be able to support the three verticals here. We want canonical representation, interpretations of this. We want the data structure to be there. And then as part of the open telemetry model, we wanted to make this as interoperable as possible. So W3C trace context, the wire formats of tracing, metrics, and logs. Fortunately, OpenTelemetry is covering all of those pieces. And this is important when we start looking at the move from what was called Observability 1 to Observability 2. So I'm actually pleased that a few months ago, we hit 1.0 as the release specification for this. So this is traces in the trace context, as well as the other pieces that go along with this, something that's usually called baggage in here. But the tracing specification for OpenTelemetry has been 1.0 for a few months at this point in time. We will be seeing catch-ups with the next pieces, and we'll talk a little bit about those as well. So now that you have an understanding of what drove this, let's look at a little bit about sort of where the architecture looks like. So open tracing kind of consists of many pieces, but it starts with an API and the software development kits, the SDKs. And these are the specifications that say how we interact as well as what we're going to be collecting for this. There's also a collector for this. And the collector is the code, the environment that lets us pull data in, process the data, and export the data to anywhere we want it to go. It is the default way of collecting instrumented application spaces and can be either an agent or a service. The collector, the open source collector, OTel collector, is widely available and is supported by most of these companies that are also in this. So for instance, we have a Splunk open telemetry collector. It is the open telemetry collector, but it has the ability that if someone went wrong and you were working with Splunk, you'd call us. We also have client libraries, and these are the application instrumentation that come into play here that today support traces and metrics for this. And they provide automatic trace instrumentation. And so you don't have to change the code to even get started making use of this. Logging is the new member, and it's in incubation. We now have logging collectors that we're working with, but they're early days for here. So as I mentioned, traces is in 1.0. Metrics is in beta. And the current languages involvements here can run the gamut from Go at 0.19 all the way up to Python. Actually, .NET is also now 1.1. My apologies for this. Java is 1.1. Python is 1.1. You can always find out the current project status if you go hit the OpenTelemetry home on GitHub. Under projects will show you what's going on with each of these pieces. So how does this all fit together? Well, this is the very simplified viewpoint of here. We have an application. That application lives on a host. That host can be in a cloud someplace. It could be a physical machine. It doesn't matter. Virtual, physical, I don't particularly care. But we put in a collector. And in this case, we refer to the collector as an agent. The collector runs on the host, and the collector talks to that instrumented library. You can actually talk to a manual if you wanted to code directly into your environment. There is the ability to do that, but it's going to talk to the data creation source, shall we say here, and it's going to ingest that data. That data can then be processed and sent out in any way we want it to approach here. We could send just the metrics pieces to one place. We could send traces and metrics to a different place. Similarly, we can have the same approach, and then we can build the same collector as a service. And so now we can have the agents sending to a service model, and the service model then carrying it forward. The nice thing about the collector is that the collector is in many ways both telemetry agnostic as well as data fluent. So you could pull, for instance, something that if you were already in tracing and had Jaeger in place, you could pull your Jaeger information into your collector, and then the collector has the ability to export that data out. And it could be in the OpenTelemetry OTLP protocol. It could be out something else. And our goal was to make sure that we were not locking anything that currently exists out, while allowing easy expansion of the capabilities within a structural block that prevents this data from ever being locked into place. So with this, however, if you remember me talking about cardinality, we also have certain things that we wanted to make sense, excuse me, that are what we call conventions, semantic conventions. And we also can deal with this. In OpenTelemetry, you can create a span about whatever you want to. It's up to the person who's creating the spans to give us the attributes that are on those operations. However, there are certain operations that are consistent across the board, HTTP or database calls. And so we wanted to make sure that these same conventions were carried forward in distributed tracing so that everyone was looking at a common language for this. And so again, HTTP, we have a method call, we have the status code. And these are just brought forward as part of the open tracing. When you receive the data, you will receive these pieces. Likewise for databases, messaging, the system, be it Kafka, be it MQTT, AMQP, whatever your piece, the messaging system is brought forward, as well as the messaging destination. Note at this point, it's not bringing in the instigation, it's bringing in the destination here. And then even if you're bringing in a function as a service, a serverless functionality, it will carry the trigger, what the driving factor to deliver to that functionality is. You can then add more functionality to this with this thing called span events. And these are similar to context-aware logging here. Every event carries timestamp information. You can think of it as a structured log if you want to. And it contains as a minimum the name of the event, its attributes that you want to carry forward, and its timestamp. And so these things that can get added directly to it. To take a look at a resource example here, the left is a Kubernetes pod, and you can see that you will get certain span information directly from that. We know what the pod name is. We know what the deployment name, the hotel collector is. We know where it came from. Similarly, looking at the right, which is a Google Cloud function, we can see what the fast ID was, the name of the functionality, and even down to the semantic convention that's saying that this was part of the central US function, and it was running in an OpenTelemetry account. This is an example looking at this from Kubernetes viewpoint. When we look at this from Kubernetes viewpoint here, our pods have our services. Each service, each pod would have a collector that's talking to that instrumented service for this. We can also have the ability to export other nodes, and we can look at this and talk to a node exporter. We can make use of Jaeger in the non-nurturing namespace, also bringing in all that collector information. And we're also talking to the underlying systems that are here, the Kubi namespace for its pieces. And over on the right, you can see, for instance, that the traces are showing that I am sending through OTLP, the OpenTelemetry protocol here. I am sending memory, I'm sending the resource, I'm collecting metrics that are Prometheus based. So all of those pieces are available to me simply from a single trace viewpoint. Now, how hard can it be to get started? Well, this is about as simple as it can get. And then I'm going to use Java inside of here. For Java, you simply drop the auto-instrumented library in place in a runtime environment. These are only runtime changes that are happening here. It provides all of the semantic conventions that we just talked about here. You can change the configuration via environmental or runtime variables here. And you can also live with manual instrumentation to the same Java environment. So you can also have your own tracing functionality and bring in this auto instrumentation. The warning, though, is don't use two different auto instrumentation solutions on the same service. I would like to say that your results are inconclusive. I'm going to tell you that your results will be broken because it's hard to understand which of the auto-instrumented pieces should be followed if you're using two services inside of this. But again, starting with Java or starting with any of those bytecode runs is this simple. Just put it in place. Starting with a auto-instrumented library that's not a bytecode run environment is simply building the library of choice into play. And there are dozens of libraries here. There are 9 major libraries that were created to begin with, but many more have evolved. This is an active open source project and is making use of the innovation in that model. So why do we want to trace things at all? Well, we need to figure out what problems we're trying to answer. And this was really designed to look at things like performance issues, how things are running slow. Today, 3.7 seconds can mean someone abandoning a shopping cart for this. 8 seconds is Microsoft's study for human attention span. But we have lots of data that's here. And because the data is unified, we can do things like move from 1 to 2. We used to have all these pieces. We could collect logs, we could collect traces, and we could collect metrics, but we didn't correlate between them. OpenTelemetry, because we're collecting them all as a single environment into a single collector, we have correlation. We have correlated telemetry so we can understand what happened from the metrics to the traces to the logs and vice versa. And so this gives us the ability to correlate across them. Now, the other piece that you may want to look at tracing is that there are some gaps that are existing. You may not be able to say what you're looking at and what's running at the same point in time. This is that confusion, that chaos that can happen inside of here. And you may not want to try to collect data in 3 different methods and try to back 3 different sources for here. Or you say simply just want to try something new. It's almost odd to talk about this, but OpenTelemetry, because of its roots in open tracing and open census, isn't really new. It's been used in production systems for a long time and is heavily in use in production systems today. But this gives us the ability. When we look at tracing, we've got some questions. Who's going to get the most benefit from this? We see SRE teams make use of this because it's easy to identify which services are involved. We find developers making heavy use of tracing because it lets them drill in and understand the user request flow and behavior every single time here. And tracing has really become more and more important because we can't guarantee a repeatable pathway on every single request. becomes the challenge and why we see tracing now in play. And finally, it helps us solve problems. So we really want to do those various things. It's your call, however, how much you trace, whether you want to trace everything or whether you just want to start with something minimum. Rule of thumb, start with your service boundaries, the calls between your services here, and third-party calls out to databases here. Add to that. It's possible to have information overload, but this is where you expect the tooling to be able to help you aggregate, analyze, and respond to it. And then finally, make the ability to get into tracing as free as possible so everybody can make use of the same information. So observability drives this thing that we call evidence-based debugging. And it's where we can start with that high-level metric, our red metrics, drill down and detangle, look at the data in the tracing environments, and actually drop all the way down into the logs to find out what the system thinks is going on in here. And once we have all that information driven by our tracing structures here, we can make the right deductions based on the evidence and take the actions to resolve any existing issues. And finally, to get started, please come join us, OpenTelemetry.io. We have a community on Gitter that's there. You can join lots of special interest groups here and consider jumping in and helping out. Good first issues and help wanting labels are widely available for that. And with this, let me close by saying thank you for listening to me and letting me be part of your event in Krakow from my 9 time zones away here. You can find me on linkedin.com as Dave Mack, and I look forward to spending some time chatting with y'all through the show. Thanks again.